All right, let's do a multidimensional or multivariable dynamical system. Just for future reference, we're doing this in April 2020, which is during the height of the coronavirus pandemic. So this is a particularly important model to us right now. So we're going to model some epidemiology, and this is a basic model for the spread of a disease. We're going to presume it's just one location, and everyone in the location mixes kind of uniformly. So we're not taking into account how some regions of a state don't really mix with other regions of the state all that much. You can add that on to the model in other ways, but for right now we're just assuming completely uniform mixing of people. So we're going to classify people as susceptible, currently infected, or removed. And I'm saying currently infected because the word infected could just mean newly infected, and we'll take that into account, but we need to think of the word infected in two different ways here. If someone is removed, we're going to presume that they're either cured and immune, or that they've passed away. Either way, they can't transmit the disease to anyone else. You can insert your standard zombie joke here. We have to think about how many new infections will occur, and how does that relate to the number of people who are susceptible and the number of people who are currently infected. So I have a simulation of it here. Here. So behind this graph, I've got a big fun simulation that puts 20 people randomly in the square 0 to 100, 0 to 100. And it puts 3 infected people randomly in the square 0 to 100, 0 to 100. And it draws a circle of radius 6-ish around each of the infected people, and then counts how many susceptible people are within a 6-foot radius of an infected person. So here there's only one person inside the infectivity radius, you could say. If I press F9, we get new random numbers, F9 on a Windows machine, or Command equals on a Mac. So let's see, not very many. I think there might be something wrong with my method here. Okay, it looks like I've got these circles drawn not quite right, but the basic idea is still going to be the same. What if I increase the number of susceptible people? Right now it's 20, let's make it 40. Do you figure that on average I'll have twice as many susceptible people inside the red zones? And if I double the 40 to 80, do I get twice as many people? If I double the 80 to 160, does it make sense that I get twice as many people on average? If I double that to 320, so every time susceptible doubles, do you figure I'd have twice as many people in the red zones? And then similarly, if I double the number of infected people, have twice as many red zones, do you think the number of susceptible people inside the red zones is going to also double? So I can bump that up a little bit. So that's our main thinking. It seems like doubling either S or I, the number of susceptible or the number of currently infected, will double the number of people exposed. So the number of interactions between S and I people is proportional to S and I. And the only way to be proportional to two things, I have it on the slide here, is to multiply those two things together and then multiply by a constant. And that constant represents, is the disease infectious within 6 feet or 12 feet? At the biological level, is it really good at getting into your cells or not very good? It also incorporates, are people wearing face masks on average, or what % of the population is wearing face masks? There's a lot of stuff that goes into that K value right there that if we were epidemiologists we would spend a lot more time thinking about. We're also going to presume that at every time step some fixed % of the infected people recover, so they move from infected to the removed. Either they recover or they pass away. There's a lot of epidemiology that goes into figuring out that number as well, but we're just going to be simple mathematicians and presume it's just one number. So at this point, you actually have enough information to go program your own Excel spreadsheet to do it all. So for a really good intellectual exercise, you can go do that. I would recommend doing 52 steps, kind of one week per step, and a whole year of steps, 52, and then graph. So I recommend going do that. To do that, you can pause the video. Pause in 3, 2, 1. All right, just in case you were tempted to watch me do the spreadsheet without trying it yourself, I'm going to distract you a little bit here and show you how the simulation works, because it's kind of fun. So I've got a list of 1,000 susceptible people here, and the x and y coordinate for each. For example, the y coordinate is just a random number times 100, so it's a random number between 0 and 1, times 100, so it's between 0 and 100. The x coordinate is a little trickier. If we're on person number 1 and I want 320 people, then it does the rand thing. But if I'm farther, let me change this to like 4 people. If I'm on person number 5 and there's only 4 susceptible people, then it gives me an NA, so that dot doesn't show up on the graph here. And then I've got 6 possible infected people here. Their y coordinates do the same thing. Their x coordinates do the same thing, where they get an NA value if I'm on person number 4 but there's only 3 infected people. And then these values are the distance between the infected person and the susceptible person, except if either of the susceptible or infected people doesn't really exist, it has an NA, then this square root computation gives you an NA. And then here, I'm saying how many of all these distances are less than or equal to a 6-foot radius. That's not quite the right thing to do, because a susceptible person could actually be within 6 feet of 2 or 3 infected people, but on average, that's a very small effect compared to the main point we're going for here. All right, so that's a little bit of fun with the simulation. So now really you should go try programming the row-by-row spreadsheet yourself, and I'll see you in the next video.